Hi everyone, thank you very much to stay with me for this long, like in the end of this presentation, in the end of this conference. So I'm Yuchi, coming from University of Michigan. Today I'm going to introduce my latest work about the analog man-in-the-middle attack. This work is collaborated with my advisor, for sure, Professor Kang Xin, and also Kyu-Han Kim from the HP labs. So the purpose of this work is going to answer one question. Is the future link-based packet source identification safe or not? But before we jump into our analysis and also our test of these questions, I will first ask you a question. How do you know the packet source for now? Apparently, you cannot rely on the IP or the MAC address because they are not reliable. It's pretty easy for the receiver or for the transmitter to change this identifier very easily in the software. Actually, this question is relatively easy in a wired network because at least you know the source of the packet, which port of the source of packet sent from. But there is no such a port constraint in a wireless network. So that's the reason, in a wireless network, any people can send the packet, just behaving it is sent from the another people. Usually this kind of behavior is called identity-based attack. And it has been shown make many problematic situations in the wireless systems for many decades. So how can we solve this problem very effectively? Particularly, there's one proposal really get a lot of attention from the industry, also the academia, is to know the packet source by how the packet is transmitted. It's kind of like a fingerprint or a biometric of the transmitter or signal itself. For example, some people say you can use the drift of this constellation to understand, to discriminate the transmitter behavior. Some people also propose, like the CSI of the devices, because we all know the CSI is different from location to location, it's different from device to devices. In a more advanced system, some people also talking about use the angle of arrival to know the direction of the packet is sent from, so we can know the packet is sent from different devices. In this presentation, we will focus on the CSI-based packet source identification. That's the one as shown in the middle range of this slide. But as we are going to discuss in the end of this presentation, the same problem is going to happen again and again, even in our scenario. So now let's talk about this link-based source identification, or we call it CSI-based source identification. Here I will give you a very high-level picture. It's a very general system design of this technology. Because we all know that nowadays there's no standardized protocol based on this technology so far. So I will just give you a very high-level picture, like most of the literature, most of the proposal always follow the same philosophy of it. Assume there's a receiver, and there's a transmitter going to send a packet to a receiver. Usually the packet is going to be validated by the crypto systems initially. Later on, once the receiver knows that's the packet from the authorized transmitter, he's going to remember the link signature of that packet in his database. Later on, if there's an attacker try to pretend, try to fabricate the packet as it sent from this authorized transmitter, the packet is going to be dropped immediately because the receiver found that the difference of this link signature of this new packet is very different from the link signature of the old authorized packet. So that's good because packet is dropped, it's stopped in the physical layer. It never goes to the up layer of the wireless system and the many problematic situations as we discussed before. I will say when the first time I read about this system, I thought it's a really genius idea because the whole system is pretty low cost. The computation is very easy compared to the crypto system. And you just need a modification on the receiver. It's usually the access point, so that's easy. That's also the reason it gets so many attention from the industry, such as if you are a company making a router, you can have this functionality and claim there's a boost of your product very, very easily. You don't need to modify the smartphone, modify your client's transmitters. But the problem is this kind of system actually, how to say that, it's can work based on many different assumptions, and I would say many of those assumptions actually will not be valid in the real world setting, as what we are going to discuss later on. Particularly, what we found is that if the attacker or the bad guy have this fault duplex relay functionality, I mean, it's pretty, it can happen in the near future, as you see many presentations we have today or yesterday, or even a demo yesterday, they all present how to implement the fault duplex relay capability in the receiver. So the things that assume the attacker have this fault duplex relay capability, the scenario will be very different. The memory guarantee provided by the system we introduced before will be break. We call this kind of attack analog man-in-the-middle attack. It's a kind of analogy of the digital man-in-the-middle attack. You know, like an original man-in-the-middle attack, there's an attacker, he tries to intercept the packet, demodulate the packet, and relay the packet again. This kind of digital man-in-the-middle attack is pretty easily to be identified by the system we talked so far, because the system we found the link signature is quite different. So that's the reason we have this attack. It's very different. We don't try to demodulate the signal. What we are trying to do is just sniff the signal at the meantime when you try to send the data and do some pre-processing and the signal and immediately relay the signal to a receiver. So actually in this case, the receiver signal is kind of a combination, it's a kind of a fuse of the link signal, of the two signals combined together. The signal, the packet is still decodable because we don't modify the payload of this packet. But the problem is that the signature for this new packet will be very different from the original authorized packet. And that's the key of this whole work. We try to inject the kind of a semi-controlled signature very stealthily in the training phase. Later on, if the attacker is going to fabricate the packet, it's behaving like a sender from this authorized transmitter. He will try his best, try to do a lot of pre-coding and pre-processing, that's the thing we don't mention in this presentation, and try to make this link signature as similar as possible as the authorized packet. So we skip all this mathematical model in our paper. We don't mention them in this presentation, but there's one very important property I would like you to remember is that no matter how hard the attacker is trying, he cannot reproduce the link signature as a good guy perfectly. There's always a slightly difference between the authorized packet and also the attacked packet. So you might ask, then in this case, how come the receiver still get confused by this technology, to get confused by this attack? The things that, to answer this question, we make a real-world trace-driven analysis based on the commercial devices. We have a lot of smartphones behaving like a transmitter, sending the packet to two commercial IP. We modify the firmware. It includes many proprietary libraries, so that's the reason we can get the full information of the CSI. What I mean is all subcarrier of the CSI we can get from these HP routers. We deploy the transmitter and the receiver in a traditional office layout, as shown in the right side of the figure. And we repeat the experiment many times over many hours in the either workday scenario or in the weekend scenario. What we found is that there are many interesting properties in the real-world setting that can make our analog man-in-the-middle attack really be a valid attack in the real world. The first observation we found is that the link signature will always need normalization. The reason for it is that the signature power actually changes significantly due to the sampling imperfection and also the automatic gain control. So here I'm going to show you in this figure, I believe it's a CSI from more than 100 packets sent from the same transmitter. And as you can see from this figure, even the characteristic of all of these CSI have a very similar structure. The scale of its energy is very different from packet to packet. Some packets even have the average energy like twice higher than the other packet. So that's the reason, as suggested by many the other literatures or my other systems, they need to make the normalization before using it as a kind of fingerprint. That actually gives us a good benefit. Because you will find that once we play with the injection power, we increase the injection power we have, then you'll find the CSI difference between the bad guy and the good guy actually going to be decreased after the normalization. So that's the first observation we found in the real world. The second observation we found is that the comparison of this CSI always need to set up a threshold. The threshold is kind of a tolerant range. The reason for it is like a Wi-Fi or a many-hour wireless system should be designed to cover a wider range of situations, such as some people might get a bad link quality in some location, and the system should also be coupled with that. So here I'm going to show in this figure is about probability is a CDF of the CSI difference over time. It's defined as a CSI of the current packet minus the CSI of a previous packet. As you can see here, we have the CSI of the two transmitter. One have a good link quality, one have a bad link quality. And if you want your access point to have a capability to get the packet from these two authorized transmitter, you should always set a threshold bigger than 2. Otherwise, you will reject the packet from the transmitter 2 with high probability. So this probability actually gives us a very good chance. It gives us a lot of room to tune our system. Because our system now doesn't need to be as good as the dotted blue line. What we want to do is just make a link signature as similar as possible. As this light blue line is showing here, it should be just located below the threshold. Then the whole system will be okay. Because now the AP will be unable to find if this CSI difference, increases CSI difference, is caused by our attack model or is caused by just natural behavior, like the topology of the environment, like if there's interference of the environment. The third observation we found is like the signature will need a periodic update, as suggested also by many papers. And here's our experiment result showing this figure. Especially in the workday environment, the people is walking around the area, the link signature is going to be changed very frequently. Like every few seconds, you should do the signature update again and again and again. Let's give us a good chance, because you remember, we play with the injection power, right? Turns out if you play the injection power too much, your system, that means the attack can be easily be caught, because the other guy will find that there's somebody just change the CSI significantly, immediately, abruptly. But the things like what you can play with, like you can keep increasing the injection power, like from 0 to some target value. And this you can, once you play with the injection power changed based on like under some tolerance range, then the system still it's not discoverable by the receiver, because the receiver is not going to know the CSI difference over time. It's caused by there's a guy trying to injection the signature, or it's just a natural behavior. Maybe there's a guy walking around in the area and they change the CSI over time. So combining all of these three factors, we found there's a pretty good chance that our system to injection the signature over time in the analog domain can confuse the receiver significantly and get a lot of degradation of the performance of the link-based source identification. So now I'm going to show you a very simple example of what we did, what we found in our analysis. Here's two CSIs sent from the two transmitter. I mean, we don't need a machine learning. Even you just look at the CSI by eye, you know they are from a different transmitter because it just looks so different. But the problem is that if you enable the MITM attack, as we suggested before, that's the CSI after this signature injection, and that's the CSI we try to reproduce the CSI as the transmitter 1 after injection. So as you can see also by eyes, the difference between this link signature after the attack get a lot of significantly reduced. I mean, they get a lot of similarity between them now. So that's the characteristic that make the receiver is unable to find out the packet is actually sent by two different transmitters. Now I'm going to give you more statistical result that we found in our analysis. The first result I will give you is about the link-based source identification performance without the attack. So we have two metrics used in this measurement. The first one is called the true detection rate. The second one is called the false detection rate. It's basically a probability the packet is classified rightly or classified wrongly. And here's ROC curve we have in our test bed. As you can see here, the system just works perfectly, and then we have a zoom inversion of this system performance. that really show the benefit, the value of the link-based source identification. As you can see here, if in the static environment, the system nearly have nearly 100% probability can distinguish the packet source. But the problem is that once we enable our take model, the system performance is degraded significantly. Remember, this dotted blue line is the original system performance. Now it's significantly moved to the diagonal line. That means that the receiver is really confused from the sender of the packet. And we also have some statistical result of the attacking probability over the location. The conclusion here is like, if your attacker is closer to the receiver, you have a higher chance to injection the signature properly and get the right behavior you want. It's pretty easy to understand because you will find like if your location is closer to a receiver, your signature injection have more impact at the receiver signal at the receiver. So we also have repeated the same experiment with some prototype validation. We don't do the very fancy hardware as what presented today in this morning by the Columbia University. What we do is just a simple 4D place implementation at the warp test bed. We use an analog placement interference cancellation to do the analog cancellation instead of specialized hardware. You basically put the antenna in the same distance and then send the signal in the reverse phase. So the signal is going to be naturally canceled at the receiver. And we also do, of course, we do some digital domain cancellation. And the packet is sent twice, so the system delay is too high for now, so we cannot relay the signal at real time. But we validated the system performance by sending the packet twice. So we get the packet as a field duplex performance, including the self-interference, and then we relay the signal again to the receiver. I will not show the result again, because the result is just similar to what we showed before. It's just a validation by the prototype setting. What I'm going to show you here is like how do you know there's this kind of attack, and how can you prevent this kind of attack? There's one important part I didn't mention in this presentation, because that's included in our mathematical model. It's the attacker needed the CSI from the good guy to him, not the CSI from the good guy to the receiver. It's the CSI from the good guy to the bad guy to reproduce the link signature of the injected signature. And it's pretty easily to be get because in the protocol we have right now, the CSI probing is standardized and it's broadcast over the air. So he just sniff the CSI probing process and he can calculate the CSI pretty easily. So as suggested also by many papers, you might change this protocol. You might have many fancy different protocols like shuffle the training sequence, like shift the position of this training sequence, or maybe some people also talking about encrypt the training sequence. But the problem of all those modifications is they take too much cost. They're not going to change they're going to modify the hardware setting of the receiver. They also need to modify the protocol design in the transmitter. That means that your smartphone. You need to modify all your smartphone to have this new security function. And also break the beauty of the link-based source identification. So what we propose here is we try to utilize the same attacking behavior, same attacking characteristic. We try to make the receiver to injection the same thing as what we did for the attacker in the CSI training phase. And then you will find, once the receiver started doing it, the related signal at the attack node will behave very differently because the attacker has no idea there's another guy is going to inject the signal in the same way. So he's going to relay this he's going to relay this, how to say that, this already injected signal again to the receiver. And based on this property, we define some prevention matrix, and it's pretty easy for us to identify if there's attack or there's not. So it's a summary of this work, like we characterized, we studied the link-based source identification, especially in the angle of a real-world setting, in the protocol setting. And then we found some very interesting property based on our analysis. So we also proposed the analog ManintheMiddle attack based on the property we found. which normally inject and recreate the link signature, try to for the receiver to make, and it has been shown able to affect the utilization of the protocol we talked so far, the link-based source identification effectively. There's some related work, but I will not go too much detail of it. I will just show some high-level example of it. First of all, part of the attacker, they want to do the same goal as us, but they have a very stringent assumption, many stringent restriction. For example, some of them assume that the CSI found a good guy to a receiver. It's no one and a bad guy, which is usually not the case because apparently you don't know the CSI, how the CSI look at the receiver. The second part of the work usually is pretty easy to be called. For example, some people they say you can injection the you can jam the spectrum, and they will stop the link between the good guy and the receiver, and then they can do some fancy things. But as you can know, if you jam the spectrum, then you will easily to be identified by the other guy because he will continue to find that there's a jamming in the spectrum. So besides of those works, I'm going to show you two very interesting parts that give us a good support of our work. The first work is about the 4-duplex relay property. That is a very famous work. It's called the Face Forward, published in SICOM 14. The idea of these Stanford students, they try to extend the coverage of the Wi-Fi in the home environment. For example, as shown in the middle area of this slide, many areas in this home topology get a yellow signal. The yellow signal actually means very bad link quality. After they deploy this relay node in the middle of the room, then they will find that many of this yellow area is turned into a red. That means the receiver signal get a lot of boost. So by the same logic, if you can think if we use the same specialized hardware as they have, but we do a different algorithm, do a different processing as we introduced in this presentation, then all of those areas turning from the yellow to red is actually the area can have a very effective injection of the signature. So that support our system, our attacking model could be very true, could be very valid in the near future. Okay. And also we talk about the system is not just limited to a CSI-based system. We also do the same thing in the angle of a rival system. And again, we get a similar thing. So once after the injection, the angle of a rival will look like the same. And it's different from the original direction, even there's no people in here, because the underlying link signature is changed significantly. And that's the end of the talk, this presentation. Thank you for your listening.